Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Izzah Binti Hanizam. My student ID is 18002274. So for my group report, my part are the summary and the conclusion. So firstly, I'm going to explain for the summary part. Fluid saturation. Fluid saturation is one of the critical parameters in petroleum engineering, which is important for variability of a reservoir. What is fluid saturation? Fluid saturation is the measure of how much the porosity is occupied by hydrocarbons. Therefore, fluid saturation is also defined as the ratio of the fluid volume in the porous medium to the pore volume of the rock. Why is it important? In petroleum engineering, information of fluid saturation is crucial because of the heavy effects it has on the relative porosity function. Inaccurate determination of fluid saturation, which can result in crossover or underestimation of hydrocarbons in place, can lead to costly error in the field. Thus, it can lead to inaccurate information of original oil in place, OOIP, or gas initial in place, GIIP. What is saturation? Saturation is defined as the fraction of pore volume that occupied by fluid, which can be oil, gas, or water. This parameter can be expressed as fluid saturation equal to total volume of the fluid over pore volume. Normally, reservoir rocks contain hydrocarbon and water, which are also referred as connect water or interstitial water. Connect water is common in all oil or gas reservoirs which surround the grain and fill the small pores. Throughout the oil and gas zone, there will be connect water distributed in addition to the bottom or edge water. Okay, fluid saturation is generally determined on small core plug samples that are drilled from the large hole core. These core plug samples are ideally assumed to contain the original in situ gas, oil, and water phase. Fluid saturation in reservoir rocks can be determined by two different approaches, which are direct and indirect. The best approach is to measure the fluid saturation from the actual physical core sample. However, there are few factors which can affect the fluid saturation determination, which are the drilling mud and the fluid expansion. Thus, fluid saturations measured in a core sample at the surface do not reflect the true saturation exists in the reservoir. What is oil saturation? Oil saturation is the fraction of the porosity of a zone occupied by oil. Most oil reservoirs contain some connect water. Oil saturation is determined using water flooding that displaces oil and water toward an observation well, forming a stable oil-water bank. Water flooding tends to leave a low oil saturation in high permeability zone and high oil saturations in tighter. Major causes of this saturation are the lithology of reservoir and capillary pressure trapping force. What is gas saturation? Gas saturation is the fraction of the pore space occupied by gas, which is studied in order to collect properties of reservoir in order to assume or estimate the reserve and control gas field development. Most gas reservoirs also contain connect water. When water moves into reservoir, the gas saturation is observed, corresponding to the amount of fixed gas. There are three special types of fluid saturation, which are critical gas saturation, residual oil saturation, and irreducible water saturation. These three saturations play an important key role in understanding the flow of multi-phase fluid in porous media and the recovery of hydrocarbon fluid from petroleum reservoir. Value of original rock saturation can be determined by using two methods that are classified to two classes, which are evaporation of the fluid in the rock and leaching out the fluid in the rock by extraction with a solvent. The two methods are Rasid method and ASTM method. In Rasid method, a sample was taken and heated as to vaporize water and oil, which is condensed and is collected in small receiving vessel. In ASTM method, this method is based on the extracting with a solvent during a distillation process by using core sample. Through this method, the water saturation can be determined, while the oil saturation will be determined indirectly. However, both methods has its own advantage and its own disadvantage.
Hi, my name is Siti Rabiatul Adawiah Binti Rasid, and I'll be presenting about the introduction to fluid saturation. So in petroleum engineering, there are three critical parameters that are significant for the viability of reservoir, which are porosity, permeability, and fluid saturation. So porosity, it can be defined as a measure of void spaces in rock, and it normally varies from 1% to 40%. As for permeability, it is the capability of fluid to flow in porous medium. The higher the permeability, the faster the fluid flow. And permeability, it is a significant parameter to determine rate at which oil and gas can be recovered. As for fluid saturation, it is defined as the ratio of fluid volume in porous medium to the pore volume of rock, which means it measures how much porosity is occupied by hydrocarbon. Moving on to the next slide. In petroleum engineering, the information on fluid saturation must be accurate because the oil in place and gas in place are calculated based on the basis of simple volumetric balance of hydrocarbon present in the pore space. If the initial fluid saturation is estimated inaccurately, this may result in crossover or underestimation of hydrocarbon in place and gas in place. And it also could lead costly errors in development field. For example, reservoir that is 50% saturated with water indicates that half of the available pores is filled with hydrocarbon. If this estimation of 50% is incorrect, overestimation or underestimation could occur, and it could lead to incorrect estimation of OIP and GIIP. And underestimation could result in development of field that is not worth developing. And if overestimation occurs, the development of a potentially viable field may be wrongfully abandoned. As for the costly errors in development field, for example, large amount of capital are spent when the reserve present are limited, and in other cases, variable pay may be overlooked because of the inaccurate assumption from inadequate saturation evaluation. Reservoir rock normally contains hydrocarbon and water, and this water can also be referred as Ganat water or interstitial water. The parameter of fluid saturation can be expressed mathematically by dividing the total volume of fluid to the pore volume. Therefore, the saturation of each fluid can be calculated. For example, the water saturation can be calculated by dividing the volume of water in pore space to the pore volume. As for oil, by dividing the volume of oil in pore space to the pore volume, and for gas, dividing the volume of gas in pore space to the pore volume. And by definition, the sum of saturation is 100%. Therefore, the saturation of water plus the saturation of oil and the saturation of gas equals to 1. So, as for the methods, there are two methods to measure the value of rock saturation. And the methods are retort method and ASTM method. So for retort method, this method is based on the evaporation of fluid, while the ASTM method is the leaching out of fluid in rocks by extraction with a solvent. These methods will be explained more by the other group members. Thank you.
Assalamualaikum and hello sir. My name is Muhammad Izzulsyahmi bin Izman, ID number 180000996. I'll be presenting the first part of literature review. The first part is the conditions of fluid saturations in the reservoir. So as you can see in the picture, there are three fluids that flow inside the reservoir, which is gas, oil and water. So actually there is two types of fluid, which is hydrocarbon and water. However, for hydrocarbon, there will be gas and oil, which indicates two different phases, as for gas, and oil for liquid phase. So, these fluids in most reservoirs are assumed to reach state of equilibrium and therefore will have become separated according to their density. Although we know that each layers were separated, there will also be connect water distributed through the oil and gas zones. So actually, instead of there is 100% oil in the oil layer or 100% gas in gas layer, there is actually slight amount of water inside it. But so actually, what is actually connect water? I will explain in the next slide. Connect water, or known as interstitial water saturation, is water that surrounds the grains and fills the small pores. In general, the hydrocarbons occupy the center of the large pores and cracks as shown in the picture. So as you can see here, the striped one will be grain, and the white one will be water, and the black one is oil. So you can see that the water are surrounding the grain instead of moving like what oil moving. So actually, water saturation depends on two factors, which is pore size and distribution, the height of the sample above the water bearing zone. Rocks with large pores such as coarse-grained sandstones, vuggy limestones, have relatively low connect water saturation. As for very fine-grained sandstone, well, they will have relatively high interstitial water saturation. That's for pore size and distribution factor. As the second factor, the height of the sample above the water bearing zone. So we can conclude that water saturation decreases as the distance from the water zone increases. So from the picture back for the previous slide, as the oil are further from water, the interstitial water saturation are lesser than the oil that closer to the water layer. Connect water saturation is important because it reduces the amount of space available between oil and gas. It is generally not uniformly distributed throughout the reservoir, but varies with permeability, lithology, and other factors.
Hi, my name is Alia Binti Razali, and I'm going to present about literature review part 2. Oil saturation is the fraction of porosity of a zone occupied by oil, or easily known as the measurement of the degree saturation of reservoir pore structure by oil reservoir. Most oil reservoirs also contain some connect water. It usually ranges from 10% to 90% and rarely 100%. To gain a better understanding, the diagram above is a zoom in, which shows distribution of oil inside a rock filled with water. On your left hand side of the slide, for the first diagram, it is the productive zone where it only contains 80% of oil saturation. For a second diagram, it is transitional zone, which it only contains 50% of oil saturation. And lastly, diagram 3, which is water bearing zone, it only contains 10 to 20% of oil saturation. Usually, oil saturation in a reservoir is determined by injecting a displacing fluid, or known as water flooding. Water flooding tends to leave low oil saturation in high permeability zone and high oil saturation in tighter. There are two major causes of this situation, which is capillary pressure and trapping force, and lithology of reservoir, which content of fine sand and silt, granular size of reservoir pore trough, and effective pore volume. Next is gas saturation. Gas saturation is the fraction of the pore space occupied by gas. Most gas reservoirs also contain connect water. When water moves into reservoir, the gas saturation is observed corresponding to the amount of fixed gas which trapped in pores. If the gas reservoir is part of a gas cap in saturated oil reservoir, the space may contain gas, oil, and water. Thus, the gas saturation varies from 30% to 90%, and rarely 100%. The importance of studying gas saturation is to collect properties of the reservoir, which is to estimate the reserve and control gas field development. Next is saturation averaging. Proper averaging of saturation data requires the saturation values be weighted by both the interval thickness and interval porosity, as both approaches use per volume weighting in averaging saturation. The generalized equation as stated in the slide can be applied to gas, oil, and water, where the symbol L is for gas, oil, or water, and symbol I refers to the subscript for any individual measurement. Like for example, if you use L as gas, so the measurement used for I is for gas also. And HI represent the depth interval to which porosity and SLI apply. This part is the type of fluid saturation. There are three types of fluid saturation, which is irreducible water saturation, residual oil saturation, and critical gas saturation. For irreducible water saturation, there are two other names that commonly used, which are critical water saturation or chronic water saturation. For the definition, it defines the maximum water saturation that a formation which is given permeability and porosity can retain without producing water, or the water phase remain immobile. Fluids in most petroleum reservoir have reached equilibrium state and somewhat separated as per their densities, which is gas on top, followed by oil and water. In most hydrocarbon-bearing formation, the rock was fully saturated with water preceding to the invasion and trapping of hydrocarbon. During migration process, the chronic water is distributed throughout the gas and oil zone due to the competition between capillary and gravity forces. The water in this zone is reduced to some irreducible minimum, that is nothing but the irreducible water saturation. This water is held in place by capillary forces and will not flow because of the tiny pore space of capillary size at the gas and oil zone. As the capillary gravity equilibrium has reached, the irreducible water saturation is generally not uniformly distributed throughout the reservoir but varies with permeability, lithology, height above free water table, and magnitude of the capillary and gravity forces in reservoir. Critical water saturation usually determined through spatial core analysis, but the fluid used must be switched where the core plug sample is flooded down to irreducible water saturation. Next is residual oil saturation, which can be defined as the oil that remains in the pore space after a displacement process. Residual oil saturation can be constructed in two ways, which is the first one is oil saturation remaining in the reservoir at the conclusion of primary production or after either the gas or water displacement process, which is normally the target for EOR. For the second ways is the final or remaining oil saturation in a reservoir rock, core sample at the end of laboratory gas displacement or water displacement process. So to determine the residual oil saturation, consider a core plug that is initially saturated 100% with hydrocarbon liquid or oil phase, and into which either water or gas is injected. The injected fluid will start replacing the oil phase from the pore space, and oil will produce from the opposite end of the core plug. Then more and more oil produced as the process continues. However, the oil production declined at certain point of time where only the displacing phase is produced from the opposite end. 100% recovery of oil from this core plug is not possible since some oil still remain trapped inside the pore space of the core plug sample that is quantitatively characterized by a saturation value that is larger than the critical oil saturation. This saturation value is called residual oil saturation. And lastly is critical gas saturation. Hydrocarbon fluid in petroleum reservoir normally exists at high temperature and high pressure condition. Hydrocarbon gas is normally dissolved in the liquid phase due to high pressure. As the production from a petroleum reservoir is initiated, the reservoir pressure begins to decrease while the reservoir temperature remains constant. The steadily declining reservoir pressure results in evolution of gas phase when pressure falls below bubble point pressure. I think that's all from me. Thank you.
Hello, I'm back. So next, we're going to discuss about how to determine fluid saturation. So we can determine the fluid saturation in reservoir in two ways, direct and indirect. The direct approach involves using preserved core plug samples, that is, small section of the rock sample removed from a petroleum reservoir. So we drill the sample from the reservoir by using the core bit. Then we take it, bring it to the lab, and we estimate the fluid saturation at the lab. So the second one is indirect method, is divided in two categories. The first one is use of some other measurements on core samples, such as capillary pressure, based on which the fluid saturations are determined. The second one is based on traditional well logging techniques, where fluid saturations are not measured on core plug, but instead are measured in situ for entire formation itself at various depths. So, the second method of the indirect is actually we don't take the core sample from the reservoir. Instead, we use the well logging to calculate the whole reservoir, the whole fluid saturation in the reservoir. So we can actually find the actual condition of the fluid inside the reservoir at the reservoir pressure and temperature. Next is factors affecting fluid saturation determination, which is the last part of literature review. So here there is two factors: effect of drilling muds on fluid saturation and effect of fluid expansion on fluid saturation. The first one is effect of drilling muds on fluid saturation. In drilling operations, a high density mud formulation is used to primarily cool and lubricating the rotating bit and to avoid the inflow of reservoir formation fluids into the wellbore. In the case of rotary drilling, the formation is under greater pressure from the mud column in the well than from the fluid in the formation, known as overbalance drilling. Therefore, this pressure gradient across the well face causes mud and mud filtrate to invade the formation, resulting in flushing the formation with mud and its filtrate, thereby altering the fluid saturation in the reservoir. And the second one is the effect of fluid expansion on fluid saturation. At reservoir pressure and temperature, most liquid hydrocarbons contain dissolved solution gas. As we know, earlier I have mentioned that there are hydrocarbons fluid and water fluid in a reservoir. When we take the core sample from the reservoir and brought to surface, the core then is subjected to different pressure and temperature. When pressure reduces, gases that initially in the liquid hydrocarbon will be released, causing the shrinkage of oil volume. In addition, thermal contraction of any oil and water present in the pore system may also be significant as the core material cools from the reservoir temperature to surface temperature. So, if we use the first method, which is direct method, we take the core sample and bring to the lab, the condition of fluid saturation during we take it at the surface condition will be different than what is actually happened, what is the fluid saturation in the reservoir. So it might be really give a big difference in fluid saturation of the reservoir itself. So we can conclude that these pressure and temperature effects result in completely altered fluid saturation in the core sample as compared to the actual reservoir. Hence, fluid saturation measured in a core sample at the surface condition do not necessarily reflect the true saturation that exists in the reservoir. That's it. Thank you.
Hi, my name is Nurul Binti Adam, and I'll be presenting the methodology to determine the fluid saturation. In previous video, what Ada said, there are two methods to determine the fluid saturation, which are ASTM method and retort method. So we go through to the ASTM method first. This method is based on the extracting with a solvent during distillation process. Based on the slide, there is a diagram for ASTM method. The material that we use is core sample, the water, the timber, and the toluene. Then the apparatus that we use is this apparatus, the electronic heater, the desiccator, the condenser, the weighing balance, and the graduated tube.
These are the methodology to conduct the ASTM method. First, a 100% water saturated rock sample was prepared. A clean and dry timber was weighted using weighing balance, and tongue was used to handle the timber. The core sample was placed inside the timber, then the timber with sample weighted quickly. The extraction flask was filled with 2/3 full of toluene, and the timber with sample was placed into the long neck flask. The ground joint fitting were tightened, but do not apply any lubricant for creating tighter joint. The circulating cold water is started in the condenser. The electronic heater was turned on and the rate of boiling was adjusted so that the reflux from the condenser is a few drops of solvent per second. The water circulation rate should be adjusted so that the excessive cooling do not prevent the condenser solvent from reaching the core sample. Then the extraction was continued until the solvent clear. The solvent can change if necessary, and the volume collected water in the graduated tube is measured. After the process is complete, the heater and cooling water is turned off and the sample was placed into the oven, and the degree is from 105 degrees Celsius to 120 degrees Celsius. And the dried sample was stored in the desiccator. The weight of the timber and the dry core was measured. The loss in weight of the core sample due to the removal of oil and water was calculated, and the density of a separate sample of the oil was measured, and the pore volume of the sample is determined. Lastly, the oil, water and gas saturation were calculated. Next, for the retort method, the material that we use is core sample and water, and the apparatus that we use is graduated cylinder, the heating element, and the condenser. The methodology are: the core sample was weighted using the weighing balance. Then the core sample was placed in the retort and the core sample was heated. Water vaporized at lower temperature 212 degree Fahrenheit, and the temperature remained at 212 degree Fahrenheit until all pore water is vaporized. After the water vaporized, the retort temperature was increased to 1200 degree Fahrenheit, and the oil from sample was vaporized and distilled. Notes: the heating element apply very high heat to a given reservoir rock sample, and both water and oil are condensed into a graduated cylinder. The volume of water and oil versus time was recorded. Then the retort oil correction is used to correct the volume of oil from cracking and cooking effects. Lastly, volume water of pores was determined, but not counting water of crystallization from clays. For these two methods, they also have the advantages and disadvantages. So for the ASTM method, the advantages is the value of fluid saturation is very accurate. The heating process does not remove water of crystallization, and the sample can be used for future analysis. And for the disadvantages is more time are required to extract all the water, and the oil saturation can be determined indirectly by knowing the weight of core sample before the test, the weight of the dry sample after the test, and the weight of the extracted water, so we can determine the oil saturation indirectly. Next, for the retort method, the advantages are short testing time are required, and the result is not accurate but just acceptable result obtained. And for the disadvantages, this process can make the water of crystallization within the rock is driven off, causing the water recovery values to be greater than pore water, as this method required in high temperature, and the oil may crack in high temperature, causing the collected oil volume to not correspond to the volume of oil initially in the rock sample, as it can decrease the liquid volume, and it also can coat the internal walls of the rock sample itself.
So that is for the summary part. For the conclusion part, one of the critical parameters in petroleum engineering which is important for viability of a reservoir is the fluid saturation. Information of fluid saturation is very crucial because the inaccurate determination of fluid saturation can cause costly error in the field. It is due to the inaccurate information of original oil in place (OOIP) or gas initial in place (GIIP). Since the two methods that are used to determine the fluid saturation have its own advantage and disadvantage, precautions are needed in order to ensure a more accurate data is obtained to avoid errors from happening in this field. That's all from me. Thank you.